Chapter 26, Sound, Mechanical Waves, Longitudinal Waves. We describe our subjective impression about the frequency of sound by the word pitch. A high-pitched sound like that from a piccolo has a high vibration frequency, while a low-pitched sound like that from a foghorn has a low vibration frequency. A young person can normally hear pitches with frequencies from about 20 to 20,000 hertz. As we grow older, our hearing range shrinks, especially at the high frequency end. Sound waves with frequencies below 20 hertz are called infrasonic, and those with frequencies above 20,000 hertz are called ultrasonic. We cannot hear infrasonic or ultrasonic sound waves. Dogs can hear frequencies of 40,000 hertz or more. Bats can hear sounds at over 100,000 hertz. Sound in air. Clap your hands and you produce a sound pulse that goes out in all directions. The pulse vibrates the air somewhat as a similar pulse would vibrate the coiled spring shown in figure 26.2. Each particle moves back and forth along the direction of motion of the expanding wave. For a clearer picture of this process, consider the long room shown in figure 26.3. At one end is an open window with a curtain over it. At the other end is a door. When you quickly open the door, as in figure 26.3a, you can imagine the door pushing the molecules next to it away from their initial positions and into their neighbors. Neighboring molecules in turn push into their neighbors, and so on, like a compression wave moves along a spring until the curtain flaps out of the window. A pulse of compressed air has moved from the door to the curtain. This pulse of compressed air is called a compression. When you quickly close the door, as in figure 26.3b, the door pushes neighboring air molecules out of the room. This produces an area of low pressure next to the door. Neighboring molecules then move into it, leaving a zone of lower pressure behind them. We say the air in this zone of lower pressure is rarefied. Other molecules farther from the door in turn move into these rarefied regions, resulting in a pulse of rarefied air moving from the door to the curtain. This is evident when the lower pressure air reaches the curtain, which flaps inward. This pulse of low pressure air is called rarefaction. For all wave motion, it is not the medium that travels across the room, but the pulse that travels. In both cases, the pulse travels from the door to the curtain. We know this because in both cases the curtain moves after the door is opened or closed. If you swung the door, or if you swing the door open and closed in periodic fashion, you can set up a wave of periodic compressions and rarefactions that will make the curtain swing in and out of the window. On a much smaller but more rapid scale, this is what happens when a tuning fork is struck, or when the speaker in figure 26.4 produces music. As a source of sound vibrates, a series of compressions and rarefactions travels outward from the source. The vibrations of the tuning fork and the waves it produces are considerably higher in frequency and lower in amplitude than in the case of the swinging door. You don't notice the effect of sound waves on the curtain, but you are well aware of them when they meet your sensitive eardrums. 26.3, media that transmits sound. Most sounds you hear are transmitted through the air, but put your ear to the ground as Native Americans did, and you can hear the hoofbeats of distant horses through the ground before you can hear them through the air. More practically, put your ear to a metal fence and have your friend tap it far away. The sound is transmitted louder and faster by the metal than by the air. Sound travels in solids, liquids, and gases. Or click two rocks together underwater while your ear is submerged. You'll hear the clicking sound very clearly. If you've ever been swimming in the presence of motorized boats, you've probably noticed that you can hear the boat motors much more clearly underwater than above water. Solids and liquids are generally good conductors of sound, much better than air. The speed of sound differs in different materials. In general, sound is transmitted faster in liquids than in gases and still faster in solids. The boy in figure 26.6 cannot hear the ringing bell when air is removed from the jar because sound cannot travel in a vacuum. The transmission of sound requires a medium. If there is nothing to compress or expand, there can be no sound. There may still be vibrations, but without a medium, there is no sound. 26.4, speed of sound. Have you ever watched a distant person chopping wood or hammering? And notice that the sound of the blow takes time to reach your ears. You see the blow before you hear it. This is most noticeable in the case of lightning. You hear thunder after you see the lightning. These experiences are evidence that sound is much slower than light. The speed of sound in a gas depends on the temperature of the gas and the mass of the particles in the gas. The speed of sound in dry air, 0 degrees Celsius, is about 330 meters per second, or about 1,200 kilometers per hour, about 1/millionth the speed of light. Water vapor in the air and increased temperatures increase this speed slightly. This makes sense, for the faster moving molecules in warm air bump into each other more often and therefore can transit a pulse in less time. For each degree increase in air temperature above 0 degrees Celsius, the speed of sound in air increases by about 0.6 meters per second. So in air at a normal room temperature of about 20 degrees Celsius, sound travels about 340 meters per second. The speed of sound in a gas also depends on the mass of its particles. Lighter particles such as hydrogen molecules and helium atoms move faster and transit sound much more quickly than heavier gases, such as oxygen and nitrogen found in air. The speed of sound in a solid material depends not on the material's density, but on its elasticity. Elasticity is the ability of a material to change shape in response to an applied force and then resume its initial shape once the distortion force is removed. The speed of sound in a material depends on the material's elasticity. It also depends on density too. I disagree with the author. Speed is very elastic. Putty is inelastic. In elastic materials, the atoms are relatively close together and respond quickly to each other's motion, transmitting energy with little loss. Sound travels about 15 times faster in steel than in air, and about 4 times faster in water than in air. Figure 26.7, the loudspeaker at the left is a paper cone that vibrates in rhythm with an electric signal. The sound sets up similar vibrations in the microphone, which are displayed on the screen of the oscilloscope. The wave on the oscilloscope reveals information about the sound. The intensity of a sound is proportional to the square of the amplitude of a sound wave. Sound intensity is objective and is measured by instruments. Loudness, on the other hand, is a physiological sensation sensed in the brain. It differs for different people. Loudness is subjective, but is related to sound intensity. The unit of intensity for sound is the decibel, dB, after Alexander Graham Bell, inventor of the telephone. The oscillator shown in figure 26.7 measures sound. Some common sources and sound levels are given in table 26.1, starting with 0 at the threshold of hearing for a normal ear. An increase of each 10 decibels means that sound intensity increases by a factor of 10. A sound of 10 decibels is 10 times as intense as sound of 0 decibels. 20 decibels is not twice, but 10 times the intensity as 10 decibels, or 100 times as intense as the threshold of hearing. A 60 decibel sound is 100 times as intense as a 40 decibel sound. Roughly, the sensation of loudness follows this decibel scale. We hear a 100 decibel sound to be about as much louder than a 70 decibel sound, as a 70 decibel sound is louder than a 40 decibel sound, because there is a 30 decibel difference between the pairs of sound each time. Physiological hearing damage begins at exposure to 85 decibels. The extent of damage depends on the length of exposure and on frequency characteristics. A single burst of sound can reduce vibrations intense enough to tear apart the organ or corti, the receptor organ in the inner ear. Less intense but severe noise can interfere with cellular processes in the organ and cause its eventual breakdown. Unfortunately, the cells of the corti do not regenerate. Drop a wrench and a baseball bat on the floor and you hear distinctly different sounds. Objects vibrate differently when they strike the floor. Tap a wrench and the vibrations it makes are different from the vibrations of a baseball bat or of anything else. When any object composed of an elastic material is disturbed, it vibrates at its own special set of frequencies, which together form its special sound. We speak of an object's natural frequency, which is the frequency at which an object vibrates when it is disturbed. An object's natural frequency depends on the elasticity and shape of the object. The bells shown in figure 26.8 and tuning forks vibrate at their own characteristic frequencies. Interestingly enough, most things from planets to atoms, almost everything else in between, have a springiness to them and vibrate at one or more natural frequencies. A natural frequency is one at which minimum energy is required to produce forced vibrations. It is also the frequency that requires the least amount of energy to continue this vibration. When you strike an unmounted tuning fork, the sound it makes is faint. Strike a tuning fork while holding its base on a tabletop and the sound is relatively loud. Why? It is because the table is forced to vibrate and its larger surface sets more air in motion. The tabletop becomes a sounding board and can be forced into vibration with forks of various frequencies. This is a case of a forced vibration. A forced vibration occurs when an object is made to vibrate by another vibrating object that is nearby. The wash tub in figure 26.9 serves as a sounding board. Sounding boards are an important part of all stringed musical instruments because they are forced to vibrate and produce the sound. The vibration of guitar strings in an acoustical guitar would be faint if they weren't transmitted to the guitar's wooden body. The mechanism in a music box is mounted on a sounding board. Without the sounding board, the sound the music box mechanism makes is barely audible. 26.8 Resonance. Resonance is a phenomena that occurs when the frequency of vibration forced on an object matches the object's natural frequency and a dramatic increase in amplitude occurs. Resonance means to resound or sound again. Putty doesn't resonate because it isn't elastic, and a dropped handkerchief is too limp. An object resonates when there is a force to pull it back to its starting position and enough energy to keep it vibrating. A common experience illustrating resonance occurs on a swing like the one shown in 26.10. When pumping a swing, you pump in rhythm with the natural frequency of the swing. More important than the force with which you pump is the timing. Even small pumps or even small pushes from someone else is delivered in rhythm with the natural frequency of the swinging motion produce large amplitudes. A common classroom demonstration of resonance uses a pair of tuning forks adjusted to the same frequency and spaced about a meter apart. When one of the tuning forks is struck, it sets the other fork into vibration, as shown in figure 26.11. This is a small-scale version of pushing a friend on a swing. It's the timing that's important. When a sound wave impinges on the fork, each compression gives the prong a tiny push. Since the frequency of these pushes corresponds to the natural frequency of the fork, the pushes successively increase the amplitude of the fork's vibration. This is because the pushes occur at the right time and are repeatedly in the same direction as the instantaneous motion of the fork. If the forks are not adjusted for matched frequencies, the timing of pushes will be off and resonance will not occur. When you tune your radio set, you are similarly adjusting the natural frequency of the electronics in the set to match one of the many incoming signals. The set then resonates to one station at a time instead of playing all the stations at once. So you have one with 19 beats per second and another wave of 20 beats per second, and when you add the waves, you have a combination of partial destructive interference situations and constructive interference situations, and you end up with this beat. And it kind of could sound like so you have this increased loudness, which is the actual beat, and then you have the decrease between the beats. Resonance occurs whenever successive impulses are applied to a vibrating object in rhythm with its natural frequency. English infantry troops marching across a footbridge in 1831 inadvertently caused the bridge to collapse when they marched in rhythm with the bridge's natural frequency. Since then, it is customary for troops to break step when crossing bridges. The Tacoma Narrows Bridge disaster in 1940, as shown in figure 26.12, is attributed to wind-generated resonance. A mild 40-mile-per-hour wind gale produced a fluctuating force that resonated with the natural frequency of the bridge, steadily increasing the amplitude over several hours until the bridge collapsed. 26.9 Interference. Sound waves, like any waves, can be made to interfere. A comparison of interference for transverse waves and longitudinal waves is shown in figure 26.13. For sound, the crest of a wave corresponds to a compression, and the trough of a wave corresponds to a rarefaction. In either case, when the crest of one wave overlaps the crest of another wave, there is constructive interference and an increase in amplitude. Or when the crests of one wave overlap the troughs of another wave, there is destructive interference and a decrease in amplitude. When constructive interference occurs with no waves, the listener hears a louder sound. When destructive interference occurs, the listener hears a faint sound or no sound at all. The listener, in figure 26.14a, is equally distant from two speakers that simultaneously trigger identical sound waves of constant frequency. The listener hears a louder sound because the waves add. The compressions and rarefactions arrive in phase, that is, in step. In figure 26.14b, the listener moved to the side so the paths from the speaker differ by a half wavelength. The rarefaction from one speaker reached the listener at the same time as compressions from the other. It's like the crest of one water wave exactly filling in the trough of another water wave, destructive interference. If the speakers emit many frequencies, not all wavelengths destructively interfere for a given difference in paths lengths. Destructive interference of sound waves is usually not a problem because there is usually enough reflection of sound to fill in canceled spots. Nevertheless, dead spots are sometimes evident in poorly designed theaters and gymnasiums, where sound waves reflected off walls interfere with unreflected waves to form zones of low amplitude, often moving your head a few centimeters in either direction can make a noticeable difference. Destructive sound interference is a useful property in anti-noise technology. Noisy devices such as jackhammers are being equipped with microphones that send the sound of the device to electronic microchips. The microchips create mirror image wave patterns of the sound signal. For the jackhammer, this mirror image sound signal is fed to earphones worn by the operator. Sound compressions or rarefactions from the hammer are neutralized by mirror image rarefaction or compressions in the earphones. The combination of signals neutralizes the jackhammer noise. Noise canceling earphones, shown in figure 26.15, are already common for pilots. Some automobiles enjoy quiet riding due to noise cancellation. Noise detecting microphones inside the car pick up engine or road noise. Speakers in the car then emit an opposite signal that cancel out those noises so the human ear can't detect them. Similarly, the cabins of some airplanes are now quieted with anti-noise technology. 26.10 beats. When two tones of slightly different frequency are sounded together, a regular fluctuation in the loudness of the combined sounds is heard. The sound is loud, then faint, then loud, then faint, and so on. These periodic variations in the loudness of sound is called beats. Beats are an interesting and special use of interference. Beats can be heard when two slightly mismatched tuning forks, like the ones shown in figure 26.16, are sounded together. Because one fork vibrates at a frequency different from the other, the vibrations of the forks will be momentarily in step, then out of step, then in again, and so on. When the combined waves reach your ears in step, say when a compression from one fork overlaps a compression from the other, the sound is a maximum. A moment later, when the forks are out of step, a compression from one fork is met with a rarefaction from the other, resulting in a minimum. The sound that reaches your ears throb between maximum and minimum loudness and produces a tremolo effect. If you walk side by side with someone who has a different stride, there will be times when you are both in step and times when you are both out of step. Suppose, for example, that you take exactly 70 steps in 1 minute, and your friend takes 72 steps in the same time. Your friend gains 2 steps per minute on you. A little thought will show that you too will be momentarily in step twice each minute. In general, when two people with different strides walk together, the number of times they are in step in each unit of time is equal to the difference in the frequencies of their steps. This applies also to a pair of tuning forks. When one fork vibrates 264 times per second and the other vibrates 262 times per second, they are in step twice each second. A beat frequency of 2 hertz is heard. Beats can be nicely displayed on an oscilloscope. When sound signals of slightly different frequencies are fed into an oscilloscope, graphical representations of their pressure patterns can be displayed both individually and when the sounds overlap. Figure 26.17 shows the waveforms for two waves separately and superposed. Although the separate waves are of constant amplitude, we see amplitude variations in the superposed waveform. Careful inspection of the figure shows this variation is produced by the interference of the two superposed waves. Maximum amplitude of the composite wave occurs when both waves are in phase, and minimum amplitude occurs when both waves are completely out of phase, like the walkers in the previous example. The waves are in step twice each second, producing a beat frequency of 2 hertz. The 10 and 12 hertz waves chosen for convenience here are infrasonic, so they and their beats are inaudible. Higher frequency audible waves behave exactly the same way and can produce audible beats. If you overlap two combs of different teeth spacing as shown in figure 26.18, you'll see a moire pattern that is related to beats. The number of beats per length will equal the difference in the number of teeth per length for the two combs. Beats can occur with any kind of wave and are a practical way to compare frequencies. To tune a piano tuner listens for beats produced between a standard tuning fork and a particular string on the piano. When the frequencies are identical, the beats disappear. The members of an orchestra tune up by listening for beats between their instruments and a standard tone produced by an oboe.